So for position versus time graph, okay, for position versus time graph, you have to understand that this is one-dimensional motion that's only moving along the x-axis, okay? So you cannot interpret this as, oh, the object is sort of like rolling down the hill and then it sort of plateaus out and then goes into the ditch and comes back. No, it's not happening that way, actually, all right? So what's happening actually is that if I were to have horizontal x-axis, okay, like so, and if this here were the positive x and this here were the negative x, and let's say that this were to be the origin 0, okay, and then this were like, I guess 4, this is like negative 4, and then like negative 12, okay. So what's happening is the object starts, okay, the object starts at positive 4, okay, it starts at positive 4, so it starts from here, and then it goes to 0, so it travels to 0 in 1 second. Then from 1 to 2 seconds, it actually stays there for 1 whole second. And then it travels negative 12 meters from there. From 2 to 3 seconds, it travels all the way to negative 12. Okay? Then it abruptly turns around and then comes to negative 4, and that's where it ends. Okay? So it starts here, goes to the origin, stays for a while, and then goes all the way to negative 12, and then turns around and comes back to negative 4. Okay? So I hope everybody understands that motion. That motion, when it's graphed, versus position versus time graph, it will look like this. Okay? So, what is the total distance that this thing travels? Well, it travels from 4 to 0 in 0 to 1 seconds. So from 0 to 1 second, right, it travels 4 meters. And then from 1 to 2 seconds, it really didn't go anywhere. Right? And then from 2 to 3 seconds, it traveled 12 meters. Now notice I am not putting any negative signs, right? I'm just putting in how much distance it traveled. And then from 3 to 4 seconds, it traveled, right? From negative 12, it went to negative 4. So it must have traveled 8 meters. So total distance it traveled happens to be just 24 meters. That's the total distance traveled. Okay? All right. Then it asks, what is the total displacement? Now, total displacement of the object from 0 to 4 seconds. So this is pretty important that you have to know your time frame, right? So from 0 to 4 seconds, what is the total displacement? Well, total displacement is just change in position from 0 to 4 seconds, okay, from 0 to 4 seconds. So from 0 to 4 seconds, this here is your initial position, right? This is your initial position. And this here is your final position, right? So change in position from 0 to 4 seconds is x position at 4 seconds minus the x position at 0 seconds. So final minus the initial, right? Therefore, the total displacement from 0 to 4 seconds is negative 4 meters, because that's where the final position is, minus positive 4 meters, right? And that comes out to negative 8 meters x hat as my total displacement. Okay? So notice the difference. The total distance I traveled is 24 meters, but the total displacement, which is change in position, is only negative 8 meters x hat. All right. Now they're asking us, what is the average speed of the object over the time interval 0 to 4 seconds, right? Average speed. Well, average speed is just v between 0 to 4 seconds. And that, notice I don't have any vector symbol at the top, right? So average speed is just v without the vector symbol, and that by mathematical definition is distance, total distance, right? Divided by the total time. Well, we already know what the total distance is. We calculated that in first part here. Therefore, my total distance is 24 meters. The total time is 4 seconds. Therefore, my average speed comes out to 6 meters per second. And that's it. No x hats, no y hats, none of those. All right? All right then. Well, what is the average velocity of the object over each time intervals above? So they want us to find the average velocity of each time intervals from 0 to 1, 1 to 2, 2 to 3, 3 to 4. Okay? So by definition, average velocity, v, right? So v average, you don't have to write down this average part, is simply delta x over delta t. If we're looking at each time interval, my delta t will always be 1 second, because it's like 0 to 1, 1 second, 1 to 2, 1 second, 2 to 3, 1 second, and so on. All right. But my delta x will be x at 1 second minus x at 0 second. And then x at 2 seconds minus x at 1 second, and so on and so on. All right. So let's take a look at from 0 to 1 second. So the average velocity from 0 to 1 second is equal to, right, x1 minus x0 over t1 minus t0. That is, right, simply x1, which is 0, that's my x1, right? And this is my x0. So 0 minus x0 is 4 over 1 minus 0 seconds. Therefore, my average velocity from 0 to 1 second comes out to, right, negative 4 meters per second x hat. Okay? Now let's take a look at from 1 to 2 seconds. Okay? For 1 to 2 seconds, we're doing the same thing, where v average velocity from 1 to 2 is equal to x2 minus x1 over t2 minus t1, right? So my v1 to 2 seconds is equal to 0 I'm sorry, not 0. Oh yeah, 0, this is x2 here. 0 minus 0 over 2 minus 1. So the velocity from 1 to 2 seconds is just 0 meters per second, x hat. It didn't go anywhere, right? So that makes sense. It didn't change the position at all. Now let's take a look at from 2 to 3. Okay, so the velocity from 2 to 3 seconds is equal to x3 minus x2 over t3 minus t2. All right, so the velocity from 2 to 3 seconds, which is the average velocity, right, is equal to x3, which happens to be right here. This is the x3, and that is negative 12. So negative 12 minus x2 is 0 over 3 minus 2. Therefore, the average velocity between 2 to 3 seconds comes out to negative 12 meters per second x hat. Then, from 3 to 4 seconds, the average velocity between 3 to 4 seconds is equal to x4 minus x2, x3, sorry. And all the x's should have that little vector symbols on it. I forgot to put it on this one, sorry. Divide that by t4 minus t3. Therefore, v at 3 to 4 seconds is equal to x4 is right here, which is negative 4. Okay? So negative 4 minus x3 is negative 12 over 4 minus 3. So 4 minus negative 12 is positive 12. So positive 12 plus negative 4 is positive 8. So v from 3 to 4 seconds is equal to positive 8 meters per second x hat. So that was all the average velocities between each time intervals. Okay. Now they want us to find what is the average velocity of the total trip from 0 to 4 seconds. Right? So from 0 to 4 seconds, my average velocity is just really nothing more than delta x over delta t. But delta x is x4 minus x0 this time over t4 minus t0, because you were looking at the total time interval right here. Therefore, since my x4, which is 4 seconds, is negative 4 meters, so negative 4 minus x0 is positive 4, right? So minus 4, negative 4 minus positive 4 over 4 minus 0 seconds. So if you do that, this becomes negative 8 meters over 4 seconds, and that comes out to negative 2 meters per second x hat. So notice the difference between the average velocity and average speed. The average speed of the total trip was 6 meters per second. However, the average velocity for the total trip is only just negative 2 meters per second x hat. Okay? So I will give you some time to finish copying this down. So we have a position versus time graph again. So don't get this confused with, going downhill and then down the drain and then staying there and so on. Okay? Again, if we were to redraw this on the x-axis, okay, it would look similar to, right? So here's your x-axis. Right? So let's understand the movement so that we are all on the same page. So here is your 0, let's say, and this is the positive x, and this is the negative x, okay? And this time, we will start at positive 1, right? So we start at positive 1 right here, and then we travel all the way to 0, right, in 2 seconds. And then in 1 second, it travels all the way to negative 3. Right? So this takes 2 seconds to go from here to here. And then it takes 1 second to go from 0 to negative 3. And then it stays there for another second. And then after that, 4 seconds, it's going to go from negative 3 to positive 3. Right? It's going to go from here to positive 3, right, in 1 second. So it ends up here. So it starts here, ends up there for the total trip of 5-second travel. Okay? So let's take a look at what's going on with the total distance traveled. For the total distance traveled, okay, I'm going to say from 0 to 1 second, I guess, it traveled, right, half a meter. So 1/2. Plus 1 second to 2 seconds, it traveled half a meter. Plus from 2 to 3 seconds, it traveled 3 meters. Plus from 3 to 4 seconds, it traveled 0 meters. Plus 4 to 5 seconds, it traveled 6 meters. So when I add all these up, half plus half is 1, 1 plus 3 is 4, 4 plus 0 is 4, 4 plus 6 is 10 meters total distance travel. Okay? All right, now let's take a look at the displacement from 0 to 5 seconds. So total displacement is just delta x from 0 to 5 seconds. That means it's just position final, which is 5 seconds, minus the position initial. So position final is x5 minus x0. So x5 is positive 3 minus x0 is positive 1. Okay. So I have positive 2 meters. X hat is my change in position or my displacement from 0 to 5 seconds. All right. Again, this is the initial position and this is the final position. All right, what about number 3? For number 3, what is the average speed, right? We know average speed is equal to just v without that arrow on top, okay? If you want to write down here average, that's fine too, right? And that is basically total distance, right? Divide by total time. Well, we already know the total distance from 0 to 5 seconds. That total distance happens to be 10 meters. Right? Total time of travel is 0 to 5 seconds is 5 seconds. Therefore, 10 divided by 5 is 2 meters per second is my average speed. Okay? Now let's do the time interval for average velocity for each time interval. Right? So for average velocity for each of the time intervals, right? So again, we can say V is equal to, right, delta x over delta t, right, which is x final minus dx initial over t final minus t initial. But we're going to do for each individual time intervals. So first we're going to look at 0 to 1 second. Okay. For 0 to 1 second, what do we have? We have v from 0 to 1 is equal to, right, x1 minus x0 over t1 minus t0. Okay. Therefore, my v from 0 to 1 second is equal to x1 is 1/2. Okay, so this is my x1 right here. And my x0 minus x0, which is 1. Okay, so this is my x0. So x0 is equal to 1/2. x0 is equal to 0. So here, 1/2 minus 0 over 1 minus 0. Therefore, my average velocity between 0 to 1 second is equal to, I get, I'm sorry, this should be 1, not 0. I knew something was messed up. That should be 1, not 0. That should be 1. All right, so that should be 1. So here I get 1/2 minus 1, and I get negative 1/2 meters per second x hat as my velocity from 0 to 1. What about from 1 to 2? For 1 to 2, again, my v of 1 to 2 is equal to x2 minus x1 over t2 minus t1. Okay? So, my v of 1 to 2 seconds is equal to, my x2 here is 0, right? And my x1 is 1/2. So here, I have 0 minus 1/2 over 2 minus 1. Therefore, my v of 1 to 2 seconds is equal to negative 1/2 meters per second x hat again. Okay, everybody following me okay? Come on, give me some feedback here. Thank you. Okay. Oh, God. All right. And then from 2 to 3 seconds, right, my V of 2 to 3 is equal to x3 minus x2, okay, over t3 minus t2. Therefore, that is equal to -3, right, -3 minus 0 over 3 minus 2, right? Therefore, my V of 2 to 3 seconds is equal to -3 over 1, so it's -3 meters per second, x hat. Okay? 2 more. So 3 to 4 seconds. So I have my V of 3 to 4 is equal to x4 minus x3 over t4 minus t3. So therefore that is equal to x4 is -3. So this is x3 and this is x4. So -3 minus -3 over 4 minus 3, and I get 0 meters per second x hat for my V of 3 to 4. And then from 4 to 5 seconds, my V of 4 to 5, right, is equal to x5 minus x4 over t5 minus t4. Therefore, x5, which is positive 3, right? x5 is the positive 3 minus -3 over 5 minus 4. So my V of 4 to 5 is equal to, this is 6 over 1. So 6 meters per second x hat for my 4 to 5 seconds. All right. All right. So let's take a look at the last part. The last part asks, what is the average velocity object over the time interval 0 to 5 seconds? Now they want to know from complete trip from 0 to 5 seconds. Okay, so velocity from 0 to 5 seconds, the average velocity, is equal to just x5 minus x0 over t5 minus t0, right? And that is x5 is 3 minus x0 is 1. Divide that by 5 minus 0. That is 2/5 meters per second x hat, and it is positive. Positive, like so. Okay? All right. Let's move on to page 22. Okay. So for page 22, we have this, looks like a crazy function here. It's going back and forth, right? So if we were to sort of like illustrate this on the x-axis, because it's only moving along the x-axis, all right? So here is my x-axis. Let's maybe I'll put it in here this time. So here's my x-axis, and this is positive x, negative x, and here's my origin, 0, and here is 20, positive 20, and then this thing is going from 0 to 20 in 2 seconds, right? So from 0 to 20 in 2 seconds, and then from 20 to 0 in 2 seconds, and then 4 to 6 seconds, I'm going 0 to 20, and then 6 to 8 seconds back to 20 to 0. So it's just going back and forth, just oscillating, right? So when we have the position versus time graph, the slope of position versus time graph represents the velocity, all right? So maybe we can write that down up here. So the slope of position versus time, right? Graph, right? Represents the average velocity between the time interval, okay? Okay, so the slope, now from here to here, the slope from here to here, the slope here, they're all going to be constant slope, looks like, from 0 to 2 seconds. So if we find the slope from one critical point to the other, we could just find the whole slope out that way, because that looks like a constant slope. So let's find the slope between 0 to 2 seconds. Somebody have a question? Aiden, you have a question? Okay. So here, let's find the slope of 0 to 2 seconds. Okay, 0 to 2 seconds. So how do we do that? How do we find slope? Well, we find the slope by doing rise over run. So rise is this, which is delta x, over run, which is delta t, right? So since slope, right, since slope represents v, right? My v between 0 to 2 seconds is equal to 20 minus 0 over 2 minus 0. So when I do this, I get positive 10 meters per second x hat for my average velocity between 0 to 2 seconds. So to represent that on my velocity versus time graph, I just need to draw a constant value of positive 10 from 0 to 2 seconds, because this slope value doesn't change from 0 to 2 seconds. So my slope value is the velocity value. Therefore, my velocity will be constant positive 10 meters per second from 0 to 2 seconds. Okay? Then, let's find the slope of 2 to 4 seconds. Okay? That is finding the velocity of 2 to 4 seconds. And that is 0 minus 20 over 4 minus 2. And that looks like negative 20 over 2 or negative 10 meters per second x hat. So from 2 to 4 seconds, my slope value, which is my average velocity value, will be negative 10 meters per second for 2 seconds from 2 to 4 seconds. Now, I know somebody's going to ask me, well, Mr. Kim, shouldn't that be like a closed circle and this be open circle and then like there should be like a dot? Yeah, if you want to do that, that's fine, you know. But I'm going to assume that you understand that already. And then similarly, if I were to find the slope of 4 to 6 seconds, it's really not that much different from slope of 0 to 4, huh? So V of 4 to 6 is equal to, right? Looks like 20 minus 0 over 6 minus 4. Therefore, if you work it out, you're going to get positive 10 meters per second again, x hat. So from 4 to 6 seconds, we have another constant slope value of 10, positive 10. So that is our average velocity value from 4 to 6 seconds. So we just draw our horizontal line at positive 10 for 2 seconds from 4 to 6 seconds. Again, if you want to like draw this dotted line here, that's fine. Open circle, closed circle. Okay? And then, last but not least, we have a slope of 6 to 8 seconds, okay? That is the velocity of 6 to 8, or average velocity of 6 to 8. And that is 0 minus 20 over 8 minus 6. And if you look at that carefully, that will be negative 10 meters per second x hat for the average velocity between 6 to 8 seconds. And then since the slope is the average velocity value, we can actually draw that here like so. And booyah, we're done. All right. Any questions? All right, so. All right, let's take a look at page 23 then. Okay. So for this one, we have it starts at positive 20. Right? It starts at positive 20 right here. And then it goes in the negative x direction for 10 meters in 2 seconds. Then it goes from 10 meters to negative 10 meters, which is now 20 meters, in 2 seconds more. Then, from 4 to 6 seconds, it stopped, stayed at negative 10. All right? So I don't have to draw the x-axis again, do I? I mean, if you want me to, I can redraw it, but you should be able to see that it starts from positive 20, moves to negative 10. I mean, moves 10 in the negative direction, and then from there it moves to all the way to negative 10, and then it just stays there. All right, so it's just going to be a straight line. So let's find the slope value of these two critical points. Now, I guess I could go from 0 to 1 and then 1 to 2, but this looks like a pretty constant slope. So I could probably go directly from 0 to 2 seconds to find the slope value. Okay? So let's look for the slope of 0 to 2 seconds, okay? Which is v from 0 to 2, which is equal to, right, x2 minus x0 over t2 minus t0, and that is 10 minus 20 over 2 minus 0. This comes out to negative 10 over 2, right? Which is negative 5 meters per second xset. Okay? So, from 0 to 2 seconds, my velocity value is the slope value, which is negative 5 meters per second for 2 seconds. So this is pretty much the graph of my velocity from 0 to 2 seconds. Now let's take a look at the slope of 2 to 4 seconds. Okay? And that is x4 minus x2 over t4 minus t2. That is equal to negative 10 minus 10 over 4 minus 2. So if you work that out, you're going to get negative 20 over 2, right? Which is negative 10 meters per second xset. Okay? So I guess all right. So if we were to graph that, so from 2 to 4 seconds, it is negative 10 meters per second xset down here. So this would be the graph of the velocity versus time function from 2 to 4 seconds. Again, if you want to put this little down here, a little up here, you know, that's fine. Okay. Now let's take a look at from 4 to 6 seconds. So let's find the slope, okay, of 4 to 6 seconds. And that would be the velocity from 4 to 6, and that is x6 minus x4 over t6 minus t4, and that is equal to negative 10 minus negative 10 over 6 minus 4, which is 0 over 2, which is 0 meters per second, etc. Therefore, for 4 to 6 seconds, we have 0 meters per second for 4 to 6 seconds. And voila. Okay? So this is what we have. Any questions? All right. All right. One more page. Yeah, this one's going to be good to know for quiz coming up sometimes next week. We'll do graphing quiz and we'll do constant acceleration equation problems separately. So we have like 2 different quizzes. So next week, sometimes next week, maybe over the weekend for the test. All right? All right. So let's take a look at this. This looks like trouble. So here we go. So again, this is a position versus time function. And this is about a wabbit, a scooey, ferocious wabbit, right? So the position of a rabbit along a straight tunnel. So the tunnel is x-axis, and it's a straight tunnel, okay? So this rabbit is not going up a side of a hill and then over the mound and down the hill. All right, so this is not like side view of rabbit running up a hill. This is actually a position versus time graph where a rabbit is only going along the x-axis, which is the tunnel, going in and out like that, I guess, right? Or it could be going out or in. Doesn't really matter, right? So if you were to think about going into the tunnel as positive x direction, so it's going in deeper, 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 stops instantaneously, comes back halfway. That's what rabbit's doing. So if you were looking at the tunnel this way, the rabbit is starting here, goes in, and then comes back out halfway. All right? So let's take a look. So the straight tunnel as function of time is plotted in figure 2-26. What is its instantaneous velocity? Now, we really didn't talk too much about this instantaneous velocity, John. But those of you who are taking calculus or who took calculus already know that instantaneous velocity can be calculated by finding the slope of a tangent line at that particular time. And to find that slope of a tangent line at that particular time t, right, you're shrinking basically the secant line of the 2 time intervals, where that 2 time interval approaches to 0 at that exact time t, right? So that is the concept of a derivative. So if you take a derivative of a position function and then you plug in the time, you get the slope value of that tangent line. So the instantaneous velocity at t is equal to 10 seconds. Well, at t is equal to 10 seconds, if I draw a tangent line to that 10-second point, it looks like it's right on this line itself. Right? So it is actually traveling at a constant speed or constant velocity from, looks like from 0 to 20 seconds. It's going at a constant speed. Because I really don't see that pink line until I see after 20 seconds. Okay? So it doesn't matter what time it is. From 0 to 20 seconds, the instantaneous velocity of this rabbit is going to be constant. And that constant value is the slope value of this pink line. All right? So, if we could find the slope of this pink line, we can find the instantaneous velocity at any time from 0 to 20 seconds. All right? Well, I really can't have any idea what this value is. It's really hard to tell at 20 seconds. I don't know what the position is. It's probably easier to estimate this right here, because I know at this time my position is 5. And that looks like halfway between 15 and 20. So if I can find the slope using these 2 points, I can probably find the slope value of that tangent line at 10. And that looks like 17.5 seconds. Okay? So this value right here is 17.5 seconds. And this here is 5, obviously. All right? So since we know, right, V is equal to delta x over delta t, right, we'll use that equation for part A. So for part A, we're just looking for the slope of that pink line. So V at 10 seconds is equal to, right, 5 minus 0 over 17.5 minus 0 seconds. Therefore, if you work this out, okay, I get 0.286 meters per second, etc. Okay? So this velocity is constant from here all the way to 20 seconds. So no matter what time I look at this, as long as it's between 0 to 20 seconds, it's always going to be traveling at this velocity. So my instantaneous velocity at any time from 0 to 20 will be 0.286 meters per second positive x direction. So voila, that's part A. All right, what about part B? Part B asks, what about at 30 seconds? At 30 seconds is right here. Right? This is the dot right here. And I have to draw a tangent line going through that dot. So it only touches that dot once. So I don't have a secant line like going through 2 dots. All right? So to do that, what do I do? Well, let's see if I can eyeball this. It's really hard to estimate this thing because it has to only touch that one little tiny spot right there, right? So I'm going to try that. I did. It only touched that one dot. Okay? It didn't touch, well, I'll try my best. All right, so your answer might be slightly different than mine, but it's okay because you have to really eyeball this. But to find the slope of this blue line, again, just like what we did here, right, gives me the instantaneous velocity at 30 seconds. Okay? The slope of this tangent line, it gives me instantaneous velocity at 30 because it only touches that 30 once. So if I pick these 2 points right here, this point and this point, I can probably work it out because this looks like it's on 35 seconds right here. And this right here looks like it's on 25 seconds. And that looks like halfway between 20 and 25. So this is 22.5. meters. And that looks like it's right on the grid line, so this is actually 10. All right. So for part B, to find the instantaneous velocity at 30 seconds, I'm going to look for that slope where here is my 22.5 minus 10, right? That's the rise, delta x, over delta t, which is 35 minus 25. That comes out to, right, 12.5 over 10 seconds. And that is 1.25, right? 1.25 meters per second x hat. So that is the instantaneous velocity at 30 seconds. Okay? What about, so here, I guess this is A, and this is B. Well, what about average velocity between 0 to 5 seconds? Well, from 0 to 5 seconds, the average velocity is going to be the same velocity that we calculated for any time according to this slope, right? And we already know that because average velocity from here to here to here to here, here to here, here to here, here to even here, they're all going to be the same value because my velocity doesn't change. So my average velocity is already calculated, and that is this, between 0 to 5 or 0 to 10 or 0 to 15, 0 to 20, 5 to 10, 5 to 15, doesn't matter. The average velocity is going to be always constant, and that is the average velocity, which is 0.286 meters per second squared. So for part C, we could write that down, I guess, right? For part C, right, for t is equal to 0 to 5 seconds, right? T is equal to 0 to 5 seconds. The slope value right is the same as value calculated in part A. Right? Therefore, the average velocity from 0 to 5 seconds is equal to 0.286 meters per second x hat. Didn't even have to recalculate that. Okay? Are we okay so far? So, for part C, all you have to do is just find the slope between 0 to 5 seconds, and it's already done for us. What about part D? Part D is from 25 to 30 seconds. So for part D, I have to go from 25 to 30. Well, look at that. 25 is right on that point, and we already went through that point. And if we know this slope value, that slope value is exactly same value as the slope value of these 2 points. So we already did this already. So even just like part C, right? So we could say for, right, t is equal to 25 to 30 seconds, right? Right. The slope value right, is the same value in part B, right? Right. Therefore, that's what 3 dots means. Those 3 dots means therefore. Therefore, right? The v average velocity of 25 to 30 is equal to 1.25 meters per second xf. Okay? And then I'm going to call this part E, okay, so that you could distinguish. Part E asks, what about from 40 to 50 seconds, right? So 40 to 50 seconds. So for 40 to 50 seconds, we have to draw a secant line. Secant line is when line goes through goes through 2 points, whereas tangent line, where the line goes through only 1 point, right? For secant line, I have to go through these 2 points right here, 40 seconds and 50 seconds. So I draw a secant line from 40 to 60, no, 40 to 50, 40 to 50 like this, and find the slope value for this red line. Okay, so this is E. So this is B. This is A. Okay. So let's find the slope of this red line right here that goes from 40 to 50 seconds. Okay. So I could probably use these 2 points. This looks like these 2 points are pretty good points to use. Okay. So we can say the average velocity between 40 to 50 seconds is equal to, right, basically x50 minus x40, right, over t50 minus t40, right? Well, x50 looks like 10 meters minus x40 looks like 20 meters. It looks like a little less than that, but I'm going to say it's close enough to be 20. Divide that by t50 is 50 minus t40 is 40. Therefore, that is equal to negative 10 meters over 10 seconds. So it is negative 1 meter per second x hat for the average velocity between 40 to 50 Okay, so negative 1. So that's E. All right, any questions? All right. All right, last section right here. So, number 7. In figure 2-26, which is the exact same figure that we used previous problem, right? A, during what time periods, if any, is the object's velocity constant? Well, object's velocity is constant if the slope value is constant, right? So when object's velocity is constant, when slope is constant. Right? So when does that happen? That looks like it only happens between 0 to 20 seconds. After that, your slope values are not constant. They're all over the place. Okay? So for part A, okay, velocity is constant, right? When the slope value is constant. Okay? Since the slope value is constant from 0 to 20 seconds, right? The velocity of the rabbit is also constant from 0 to 20 seconds. I hope that's not too wordy, but okay. What about part B? At what time is the velocity the greatest? Well, the velocity is the greatest when the slope value is the greatest, right? So for part B, now I'm going to assume that they're talking about positive velocity because there could be positive velocity or negative velocity, right? So if you look at this, I mean, this looks pretty steep here compared to this. But if I were to look at like 27 seconds, that tangent line is steeper than 30 seconds, right? Here it's not as steep at 26, but like 27 and 28, it looks steeper. So it looks like 27 seconds is where is the greatest slope value, which means it's the greatest velocity value. Now, as far as here, this can also be it, I guess, like around 45 to 46 seconds. But I don't know exactly how much steeper is that compared to this. And this is also a negative velocity. So as far as the positive velocity is concerned, I'll say it's around 27 seconds. Okay? So since the slope value looks greatest at 27 seconds, right? Maybe I could say positive slope value, I guess, if you want to. Positive slope value looks greatest at 27 seconds, right? At 27 seconds, the velocity will be the greatest. Boom. All right, what about C? What about C? C states, since the slope value, okay, well, at what time, if any, the velocity is zero? Well, velocity is zero when slope value is zero. And that can happen only at right around here, because if I do a tangential slope line, that's the only time where it's going to actually have a zero slope. Right there. Right? That means my instantaneous velocity is zero at this time, which is around 37 seconds or 38 seconds. All right? So, since the slope value, okay, right, of the tangent line at 37 seconds is zero, okay, the velocity value is also zero at 37 seconds. And for part D, does the object run in one direction or in both along the tunnel? Well, that's kind of obvious because it runs in this way, stops instantaneously, turns around, comes back out halfway. All right. So the rabbit, right, runs in positive direction from 0 to 37 seconds, right? Then at 37 seconds, it stops instantaneously, right? Then runs in the negative direction from 37 to, I guess, 50 seconds. All right, my voice is shot. My throat is hurting. I hope that concludes our lesson for today. Any questions? All right. Oh, God. Did we go overtime? I'm sorry, guys, for keeping you here so long. Have a wonderful weekend, and I'll see you guys on Tuesday. All right? Thanks. Bye. All right.